All right, so let me just continue my tour of the zoo of discontinuities. And I guess I want to illustrate something with the convenience of right and left-hand limits. So I'll save this board about right and left-hand limits. So a third type of discontinuity is what's known as an infinite discontinuity. And we've already encountered one of these. I'm going to draw them over here. Remember, the function y is 1 over x. That's this function here. But now I'd like to draw also the other branch of the hyperbola down here and allow myself to consider negative values of x. So here's the graph of 1 over x. And the convenience here of the distinguishing the left and the right-hand limits is very important, because here I can write down that the limit as x goes to 0 plus of 1 over x. Well, that's coming from the right, and it's going up. So this limit is infinity, whereas the limit in the other direction from the left, that one is going down, and so it's quite different. It's minus infinity. Now, some people say that these limits are undefined, but actually they're going in some very definite direction. So you should, whenever possible, specify what these limits are. On the other hand, the statement that the limit as x goes to 0 of 1 over x is infinity is simply wrong. Okay? It's not that people don't write this. It's just that it's wrong. It's not that they don't write it down. I mean, in fact, you'll probably see it. And it's because people are just thinking of the right-hand branch. It's not that they're making a mistake necessarily, but anyway, it's sloppy. And there's some sloppiness that will endure and others that will try to avoid. So here, you want to say this, and it does make a difference. You know, plus infinity is an infinite number of dollars, and minus infinity is an infinite amount of debt. They're actually different. They're not the same. So, this is sloppy, and this is actually more correct. Okay, so now in addition, I just want to point out one more thing. Remember, we calculated the derivative, and that was minus 1 over x squared. But I want to draw the graph of that and make a few comments about it. So I'm going to draw the graph directly underneath the graph of the function. And notice what this graph is. It goes like this. It's always negative, and it points down. So now this may look a little strange that the derivative of this thing is this guy, but that's because of something very important, and you should always remember this about derivatives. The derivative of a function looks nothing like the function necessarily. So you should just forget about that as being an idea. Some people feel like if one thing goes down, the other thing has to go down. Just forget that intuition. It's wrong. What we're dealing with here, if you remember, is the slope. So if you have a slope here, that corresponds to just a place over here. And as the slope gets a little bit less steep, that's why we're approaching the horizontal axis. We're getting the number's getting a little smaller as we close in. Now over here, the slope is also negative. It's going down. And as we get down here, it's getting more and more negative. As we go here, the slope, this function is going up, but its slope is going down. All right? So the slope is down on both sides. And the notation that we use for that is well suited to this left and right business. Namely, the limit as x goes to 0 of negative 1 over x squared, that's going to be equal to minus infinity, and that applies to x going to 0 plus and x going to 0 minus. So both have this property. And finally, let me just make one last comment about these two graphs. This function here is an odd function. And when you take the derivative of an odd function, you always get an even function.